Welcome everybody. My name is Nils Thüray. I'd like to welcome you virtually to the Game Physics lecture of the TUM Games Engineering Bachelor. As you're aware, and I guess not too surprisingly, unfortunately, we have to do this fully virtually this year. Hence, we probably won't be able to meet in person in the foreseeable future, although I hope that at some point over the course of the semester we can either meet virtually or maybe at some point have some events on location. But for now, the lecture will take place via these recordings. And today my main goal is to actually explain the structure of the course, what to expect over the coming weeks from this series of lectures, and to also give you a bit of an overview of the contents that we'll be talking about. So with that, I'll move into the corner here and start with the slides. Yeah, so let me start with the lecture itself. Oh, great! So this is now hiding the email addresses. Well, actually, this is just a recording. You'll be able to find the slides as a PDF. Nonetheless, this is my email in case of questions. And now, for the lecture itself, these recordings, you've already found the first one, obviously. They will be provided on Moodle as the rest, the slides as well. And the format of this lecture will actually be that the lectures themselves will be pre-recorded, and we will have a Q&A session at the time slot of the regular lecture, so that is Monday at 10. How to join, please again check the link that we provide on Moodle. So the idea is that please look at these lectures beforehand, and then ideally take notes of the questions or the topics that you'd like to discuss, and then join the Q&A session where all people that are interested, or also actually all just who are interested in listening in to questions that others might have, can join in, and then we can discuss the open topics in this session. Yeah, so so much for the lectures themselves. The exercises are worth a few more comments. So these are actually a pretty important part of the class. In a way, it is my opinion that you only really learn things if you're doing them. And for these computer simulations, that means that in order to really learn how they work, you actually have to write and implement some simulation algorithms. And over the course of the semester, we actually have three fixed exercises regarding certain types of simulations, and then a free project. So the person responsible for these exercises is you. You can see his email here in the corner. The idea is that these exercises will be handed in groups of 3 and 4, or 3 to 4 people. That is primarily due to the number of groups that we handle. However, again, the kind of goal of these exercises is that you actually do something yourself. So I can only highly recommend that you actually spend the time and really work this out yourself. So ideally, I would recommend that every member of a group goes ahead and really does all all of the parts of an exercise, and then later on you discuss and merge this into one final solution. But what should not happen is that person 1 does task A, person 2 does task B, and person C task C. Then each of you only did a third of it, and hence you probably only learned 1/3 of the contents of an exercise, and that is not the point. These exercises are not mandatory, right? We're at a university, we're not forcing you to do this, but if you want to learn the content, then I think the only way to do this is to really do all of these things yourself. Unfortunately, over the past years, we've had that very often that there are groups where, in worst case, one person does everything and another 3 persons look over the shoulder of the first person and nod, basically. No, yeah, sure, that's how it works. But if you haven't done it yourself, if you're looking over someone's shoulder, I can promise you won't learn much. And that typically latest shows in the exam, but also it will show in the next years. So if you really want to take something out of these exercises, I think it's crucial to really do this yourself. The tasks themselves are actually C++ based. We will give you a framework. The details will actually start next week only, so don't worry about that for now. We will give you the details where to get started and the instructions in the following week. But yeah, we're basically providing this framework again to have a common ground. You could deviate from that if you like a bit, but right now it's mostly Windows based, and at least for the submission we actually require basically handing it as part of that framework. Typically 2 to 3 weeks. We have a set of tutors who support these exercises. There will not be any specific tutorial sessions. Rather, the tutors actually will have slots where they just support your work on these exercises in case you have questions or you're stuck somewhere or you don't understand a part of the instructions. Then please get in touch with the tutors. Although we will try to offer some additional tutorial explanations over the course of the next weeks, detail to follow there. Right, for the exercises, after these 3 given tasks, is one open project, typically a combination of the previous works. And then at the very end, we will actually have an exam session where you get to present these projects to the other groups. And then we also need to double check that you personally worked on this in order to give a 0.3 grade bonus. This is a bit due to the TUM regulations. We have some limits of what we can legally basically do here. But yeah, whenever we have an exercise that impacts the grade, in this case also only when you actually pass the exam, so it cannot move from a fail to a pass with this grade bonus. But if that's the case, we actually need to be able to attribute it to a single person, so we cannot let you hand in as a group, then say, oh yeah, all of you get the bonus. Rather, we have to individually check that you worked on this, and right, this is actually another good reason to do this yourself, because in the end we'll actually ask you about the content of all of these exercises, and unfortunately we regularly have people that come at the very end of the semester and then join the session, and then they cannot answer any questions about how this worked. So please actually do these programming tasks so that you learn from it and that you also later on can answer these questions. And yeah, also needless to say, but the exercise, the content and what we ask there is tailored as a preparation also for the actual written exam. I'll come to that in a moment. You'll see there typically also in some cases some pen and paper calculation tasks, which are actually geared towards what then might be asked in an exam. Yeah, I can also encourage you to organize your group, so to meet and discuss. But in the end, every member of a group really should know all the details, and I can recommend that every member really works out the individual solutions. But of course, it would be great if the members of the team also support and help each other out. But yeah, so as mentioned before, this will really start in the coming week. So the only task I can right away give to you is that this is November 9, that's the date where details will follow. One thing you can already think about though is, as mentioned before, they will be handed in groups. So one of the first things to basically determine is in which groups to work. Please start asking around, see who you might want to form a group with, or if you do not have a group, directly, for example, send an email to you. And that's fine, of course. If you don't have partners for a group yet, let us know. Or people who cannot form a group, we will combine or put you in touch so that you can form groups. But normally, also the lecture is a very good point where everybody comes together and then afterwards you could easily discuss. Obviously not possible right now, but definitely start thinking about it. And if you're not sure, or if you're short on colleagues to form a group with, then please get in touch with us right away. Yeah, also a popular and important topic is the exam. So what's important to note here is we will have a physical written exam. So the exam, we actually, due to its structure, have to do on location. So please plan ahead. This will be mandatory. We will not be able to offer any separate remote examination setups, but you will need to be in Munich for the exam. We do not have a date so far. We cannot choose, right? They assign a date to us and we don't know it yet, but tentatively February to March 21. So this is actually next year, of course, so in the year 21. And it will cover the contents of the lecture and also the topics discussed in the exercises. So typically around February next year and on location a physical exam. All right, another topic to mention here is we have some books to recommend. So actually this one's a nice, relatively basic book by Ian Millington. This is a fairly nice and easy read that gives, this one actually focuses on rigid bodies, but nonetheless also covers some of the basics. There's a very good introductory material, so a good starting point I can recommend. I'll also get back to that book once in a while in between. Or alternatively, this O'Reilly book is also a fairly neat one, just to offer an alternative. What I cannot fully recommend, it's somehow very popular if you search online, but there's this game physics book by David Eberly. This one is a bit more in-depth and a bit more mathematical, so I can recommend this as kind of further reading if you're interested, but this probably will not be the best one to prepare you for the exam. Yeah, then also what's a good thing to discuss at this point, a bit related to the exercise topics, right, there's a difference between learning and teaching. So teaching, that's my responsibility, especially myself, but also my team. Basically, it's our duty to support you and to provide you with materials. That's the teaching part, but the learning part, that has to happen on your side. So we cannot make you learn. That is your own initiative. We can only give you the materials and encourage you, like by encouraging you to do exercises yourself. That is what actually will make you learn. Right? Learning by doing is crucial. And we try to set up a learning environment. In the end, the learning is the responsibility that lies with you. Our responsibility is the teaching aspect. Yeah, nonetheless, of course, if you have suggestions for improving that, please let us know. We're open to new ideas there, especially now with the slightly changed situation. This is the first time that the game physics course specifically is being held online, but as far as we can foresee, hopefully that translates nicely to the online setting. Yeah, so let me put the topics a bit into the context. So we are part of computer science, right, or informatics, as my colleagues here in TRM like to prefer to call it. So computer science actually has a lot of different fields by now, right? It's really ubiquitous in our environment, thanks to things like mobile devices and so on. We have it everywhere, starting from theory, databases are classical topics, networking, or algorithms. But what in a way is closest to what we'll be dealing with is computer graphics. So showing, visualizing things in the computer, and that by itself also has, drilling down a variety of subfields. The classical one being to display things on screen, the rendering aspect of it, which actually will play a minor role in the game physics setting. We typically will produce something that will be shown on screen, but we will not deal too much with the question of how to really show it realistically. That is more a question of rendering algorithms. And actually, if you think about it, in a way, rendering is also physics simulation, basically how light bounces off inside of a scene, how it reflects and refracts on complex surfaces. But yeah, we will not deal with these simulations so much, but rather with motions over time. Geometry is another crucial aspect. How do we actually describe a certain shape, three-dimensional shape in the computer? Also non-trivial. Here you can see one example, one answer that's very popular, and that is the good old-fashioned triangle. This is one of the primitives. Right, this is nice for a surface, and if you want something in 3D, then we need a tetrahedron, and in 4D, it's a bit more complicated. But dealing with surfaces in 3D, triangles are, for example, a good representation. But this is also not a trivial question what to choose and how to best work with geometry under certain constraints or application settings. What we'll be dealing with is animation, so meaning we're interested in not only some static geometry, but in how do things actually change and move over time. And drilling further down, there's a variety of different ways to approach that, from manual specification of motions to mocap. But the goal of this course is to leverage physical models to move things over time. That would summarize as the main goal of the algorithms we'll be talking about, which you can actually see as a kind of specialized procedural way of animating things. Yeah, it's also good to think about. Animation is actually an old word. It comes from breathing life into it. I think it's a nice thought. and hence also traditionally characters, right? Here's a good example from Monsters University, are a target here. However, I'll come back to it in a moment, we'll be dealing typically with non-animate characters, so materials rather than characters who act on their own, rigid bodies or things you would find in your environment, at a wall basically, things like that. Yeah, what also plays an important role in this setting is for interactive applications. We typically have situations where a player or user inputs commands and has a large flexibility with respect to what he or she can do. Hence, we typically cannot just pre-compute or manually create all the different aspects of it, but we need to compute on the fly, and in a way, this is where the physical laws come in, where they're so great, because these physical laws, right, think about Newton, they are not tied to a specific application or one specific setting, but they're really fundamental laws of how our nature behaves. And as such, if we can compute these, then if we do it right, we also can very flexibly deal with all kinds of situations in a computer. So this is where the simulation aspect comes in. In a way, it's kind of leveraging these fundamental laws for general and flexible simulations. Well, we do need to compute it right there on the spot with a certain frame rate while the program is running. So there is an inherent trade-off, and as one of the topics we will be getting back to a lot, we need to make sure things are fast enough to actually run in essentially real time or even much faster, and that is a bit of a trade-off between how accurately we can compute the solutions while actually ensuring stability. Right? The nicest simulation does not give me anything if it's blowing up and not showing on screen. Yeah, also beyond traditional computer games, these physical simulations really do play a large role in a variety of literally all kinds of interactive settings, whether it's training applications. Think about medical simulators where people need to understand certain behavior of how tissue behaves. So people learning about physics, being able to interact or kind of virtually run virtual experiments, or the game setting to basically entertain people. This is another nice way to think about it, a bit similar to the point I had before. You can think about animation or the modeling of content in interactive settings in terms of this pyramid. At the very bottom, we have the geometric aspect, right? So purely describing the shape of the pyramid or so. Then we can compute kinematics in a way, pure forward motion over time, and we will be targeting this middle level here, the physical level, where we have physical laws that tell us about interactions, changes to the environment. The next layer of complexity here, but also the physics is not the end, right? If you think about, as mentioned before, going towards characters, we could, based on these physics, then start to model behaviors, having agents with certain own goals and behavioral aspects. And traditionally, what you could see as the last bit to close these models is to also model the cognition of these agents. So, right, like us basically seeing, being able to touch and feel certain parts of our environment, and letting the agents interact with the physics based on their behavior and their own cognition. But here we will actually focus on the center level. Yeah, let me explain a bit more these different ways to do animation. That's also worth a few comments to motivate a bit why these physical models are interesting and important in virtual environments. So one of the most traditional ways to move things, especially for example for movies, is a keyframe animation. So here's a nice example of a ball. It's essentially a bitmap, and we place certain keyframes over time. If we're smart, we don't place one for every single frame of a 100-frame sequence or so, but we place a few and then interpolate a smooth trajectory across these. But nonetheless, this is a very manual process. So in a way, that's great. We have full control. We can very exactly specify for every instance in time where this object, this ball, should be. But this is pretty tedious. I'm sure you can imagine if I have a single ball, it might be okay. You can let that bounce around. Even then, it's sometimes not even that easy to really get it right, but this is definitely not interactive. Right? Then I have one fixed trajectory. This is very difficult to make it flexible, but nonetheless a traditional way and a very controlled setting. As mentioned before, motion capture is another interesting aspect. I have to move a bit. So here the goal is that, or the kind of starting point is that we start with a real person or object, some real thing that we want to capture. Traditionally, we put markers on it. These technologies have improved quite a bit, but nonetheless, we somehow need to track points on the object. Those are reconstructed in 3D in the computer. As you can see in the second picture here, and giving some kind of rough skeleton. This we can transfer to some rigged model, for example, of a character, and this rig would then drive the actual mesh, kind of more or less smoothly interpolated hull for the rig. And yeah, the nice thing is now we can really get data from a real performance. What's a bit tricky is that this produces a lot of data typically. It needs to be cleaned up and worked with. And what if we want something crazy, like a flying elephant or a dragon or so? That's difficult for a mocap setup. So in a way, it also restricts us to things we can actually capture in reality. And again, this is not interactive. I get a real performance, but if I want to make this interactive, I basically have to really go in and capture every possible behavior that I might anticipate in a game, which is actually what many of the sports games did. They have vast libraries of motions, but again, this leads to a certain authoring and capturing workload beforehand. Yeah, this is in a way where the physics nicely come into the picture. So physics-based animation now uses these very generic laws and lets us then vary the behavior based on these principles. So here, the picture is a very classic one, rigid bodies. If we choose the right ones, the right physical models, then we can actually compute it in real time, but typically this requires quite some calculations, so this is potentially much more expensive than the others, where we basically play back some pre-recorded data. And the nice thing is now we can let forces or situations flexibly change here within that physical setting. We will just get a different solution, but this is in a way no problem for such a solver, right? If we can afford to compute them on the fly. Yeah, looking ahead a bit, what I think is now actually a very interesting outlook, especially to reduce the complexity of the real-world physics, is to have learned models that capture the most important bits, and for example, to use neural networks as function approximators, giving us solutions to these physical models. This is actually a very interesting research topic that I'll come back to once in a while over the course of the lecture. We will be focusing on the kind of traditional way of modeling from known physical laws and finding solutions. In a way, these machine learning applications are a step on top. In practice, it's typically not a good idea to use any machine learning if you don't know what you're dealing with. So even if you're interested in going towards kind of deep learning driven physics simulations, it's typically important to know about what would a normal model and a normal solver do to make the transition to a learned one, like in other fields for learning. But nonetheless, I think it's a very interesting outlook. Another note that's important here is that by physics here, of course, we don't mean basically don't mean everything you would normally deal with when studying physics at UM or so. Right? So what we are dealing with here is actually one very specific field of physics, namely traditional mechanics. That's what we'll be focusing on here. Nonetheless, this is also part of a physics track typically, but we won't go into other topics like astronomy or electronics or so. There's all kinds of topics around this that could be interesting in a physics setting. So we'll be focusing on mechanics. Nonetheless, I think a very interesting aspect of physics. Yeah, now I have a bit of a summary slide to summarize the goals of this lecture. Right, so in a way, for the immediate topic of game physics, interactive physics, is we want to create a believable interactive world. In the setting, it's actually believable is crucial. We can simulate a lot, but if it blows up, if it goes wrong, that can really hurt. It can have the best graphics. If it does garbage, if the behavior doesn't match, that can hurt the reality. So it's important to really make it believable. And this is also then something that's really powerful to be explored by players. I have some examples later on. This can lead to or can provide a very nice basis for creating fun and nice gameplay. Or also it can actually reduce the amount of work to create a game. Again, later on I'll show some examples of games with physics, and in a way a physics simulator often can allow you to provide a large variety of behavior without actually having to manually create each of these different instances. Yeah, so we'll be following on numerical simulation algorithms. So actually one of the alternate ways of summarizing summarizing the goals of this lecture is like cool stuff you can do with numerical math. Hopefully you'll see quite a few examples over the course of the next semester. We'll deal with efficiency and stability. Also, it's traditionally a crucial topic within numerical simulations and one that we come back to a lot. And then also, being part of the bachelor track here in games engineering, we actually want to also incorporate a few very practical aspects, right? How do we get these things into working implementation? Yeah, those are the main goals of the course, and I want to give you a brief overview and outlook of the different topics we'll be dealing with, and that's kind of the summary here. Yeah, I don't need to read this, I'll just show you a few examples. So the starting point that we'll start with later today actually is starting with particles, right? That's in a way the simplest representation of a physical object in the computer. So we're just storing a position. So down there you can already see a small mock-up. We're basically assuming we have a infinitely small point that just, we know its location. Typically we also have a vector that specifies its velocity, for example. It might have a mass and some force acting on it. But these are typically very simple models. And in a way, what allows us to do very large particle systems is that typically they don't interact. So every particle is in a way alone. It has a few properties, but it just flies through space with some forces acting on it. It doesn't talk to its neighbors. And in that way, right, we can in parallel typically process very large numbers on the orders of many millions of particles. And here I have a nice small movie of some traditional particle systems from a particle system demo. Down there in the bottom you can see all kinds of stats of the current system, and I don't want to go into details what you're seeing here, but all of this is based on just on the order of a few hundred different points that act to relatively simple laws, right? Some kind of driving force or some pre-specified motions. And then in this case it's actually neat because typically there's some kind of transparent billboard that's displayed for every particle, and that gives some surprisingly nice patterns. So here with these fire particles and a small animation, they change the color from yellow to gray, and that already gives a fair amount of complexity and interesting behavior. And in a way, right, key for making this interesting is there's a large number of them, quite a few. The next step towards getting more interesting, more complex behavior is to make the particles less alone. So next, what we'll also introduce in the lecture is to have a connection between selected particles. So springs. Here on the right you can see a small mass spring system with 4 particles and 3 springs connecting them. And from that suddenly now, instead of having isolated single particles, even if there are many, now we really have something to describe a volume and interactions in a volume. So typically not easy. There are all kinds of questions with respect to how to place, how to arrange them, how to keep these stable, but nonetheless there are really interesting effects that you can do here. And here's one nice example. Not a volume yet, but this is now a closed surface. This is a piece of cloth that collides with these spheres and falls over them and gives some pretty complicated behavior. As a kind of variant to model or for modeling 3D objects, we'll introduce rigid bodies. In a way, for rigid bodies, suddenly now we're taking things away. Now we don't have a lot of points that can move relative to each other, but for rigid bodies we assume it's fixed. We basically have something like a box or so that does not change, but just moves rigidly, hence the name. In a way, this is an interesting variant because if we do it right, if we change the physical model to incorporate this rigid motion, we can suddenly get very complicated behavior very efficiently. And this is what we'll be dealing with here. Again, there are some tricky questions like how to deal with collisions, collision responses, and stacks of objects, but nonetheless, this in a way is a good next step after the mass spring systems. And that is also a very traditional topic. I'm sure you've seen quite a few examples. This is a very old one by now. So this was possible roughly 15 years ago already. And despite being so old, the fun about such simulations is As you can see here, we can run a lot of them and then might have things like these crumbling towers of stacks of rigid bodies and get all kinds of complex behavior. So here, these are several hundreds of these boxes flying around. Slightly newer example, this is only 10 years old or so, from Bullet, one of the classic rigid body, real-time rigid body engines. So what's interesting here now is, compared to the previous one, now these demos actually couple rigid bodies with mass spring systems and or constraints, and suddenly you can actually get very complicated behavior, like this piece of rubber coupling the two rigid bodies, or you can imagine having kind of rubber ropes that constrain the motion of the bodies. And a few more examples will follow. In a way, this is another step of complexity that we will not fully deal with in this lecture, coupling different types of simulations. This is a bit what you can explore in the project towards the end of the semester. We'll mostly be targeting the individual pieces for certain types of physics, like rigid bodies or mass spring systems. Okay, this example is not so exciting now, but there's more coming up. Right, this is just a non-extensible cloth. So this is the example I was looking for. Here we have now several rigid bodies with the strings and some deformable tori in the mix. So well, you can imagine if you go towards this direction, it can be quite complex in terms of behavior and also in terms of computations. Yeah, moving towards more and more complex physics, we'll also talk a little bit about fluids in this lecture, because this is actually a surprisingly tough topic, because in a way it's almost the opposite of a rigid body. For something like a glass of water or splashes or so, there's actually no clear shape at all. Water can deform in any way you let it, basically. Whereas a rigid body, it is fixed in its behavior and does not change at all, according to the model. And one classic example here is this one. This is a classic rigid body simulation, so one of the very first interactive ones. You can still see the individual particles that were used to simulate it. In a way, now we're back to particles, but here the main difference is that all of these particles, at least in neighborhoods, constantly need to talk to each other and evaluate pretty complex functions in neighborhoods of all the particles. So this little glass of water is actually, in a way, surprisingly complex to simulate. Play it again. So this is actually now already tricky to get fast in real time. But later on we'll be talking about as a kind of continuum model and perfectly plastic deformation. We'll also look at fluid simulations in this particle-based setting as an outlook. And right, this is actually, now it doesn't look so nice, but within these modern techniques you could make this look quite impressive. I also have a nicer example later on. This is kind of historic simulation. Yeah, and with that, I'm already at the end of the first part. Normally, I'd like to take questions now regarding structure or content of the class. If you have some questions, please write them down for now, keep track of them, and join the Q&A session on Monday at 10, and then I'd be happy to answer these questions during the session. Or alternatively, also these Q&A sessions will be the main part where I'll be able to answer questions. If you have questions in between regarding the exercise structure or groups, then you is the right person to contact. You have the email address in the slides. Or later on for specific questions regarding the individual assignments of the exercises, then please get in touch with the tutors. All right, but thanks so far.